Welcome to the first session of the morning. The first speaker will be Alan Prince, speaking on metrical theory as a portal on theory.
Let me make a brief housekeeping remark. Donka kindly informed us speakers that we could use the 45-minute period as we wished. So I have a tripartite argument, and I would like to make the argument and then open the floor. So I will proceed organically in that fashion. Let me begin by saying how delighted I am to kick off this celebration of Morris Halley's works and days. It is his broad shoulders on which we stand. And I'd also like to remember Jean-Roger Vergniaud, our friend and colleague, who I think would enjoy the view of what we can see now. So let's take a look and see what there is to see. So I'm going to talk about recent work with my colleagues, jointly and severally, Birgit Alber and Nazare Merchant. And I'll refer variously throughout to stuff we've done. Okay, I'm going to try to advance and demonstrate three theses. First is that an OT typology comes with an intrinsic geometry that influences how its languages class together. So I'm going to be investigating the issue of how the languages of a system group together into classes illustrating fundamental properties. And the geometric result is that geometric contiguity is required for this to happen. And here's an example of a geometric representation of the target typology, the grand target, which we will allude to but only make steps toward today. This is a stress typology of 21 languages using a type of constraints that I'll introduce in a minute. And its distinguishing characteristic is that it allows completely unparsed strings as candidates. If we disallow those and only use them, only allow monosyllables to be unparsed, things simplify like this. And if we go a step further and generalize across these classes, ignoring distinctions of foot type and directionality, we get a geometry like this. And this is, of course, the kind of geometry we'll actually be studying today. Okay, a second hypothesis, and it's not really a hypothesis, it's a demonstrated property that we'll see how it emerges. An OT typology comes with an intrinsic order and equivalence structure that determines how its languages class together. Now, this is not an order on candidates of the type we're familiar with, which is used in optimization and so forth on a daily basis. This is an order on languages. So we'll see that each constraint imposes a kind of order structure on all the languages of the typology. And the result is, the classification result is that the defining properties of order must be preserved by generalization, which will reduce graphically to a perspicuous condition that no cycles may occur in the graph. So what does the graph look like? Well, this is what the graph of the full system looks like. If we look at the simplified system that we were just talking about, its graph looks like this, and another simplified system worth discussing looks like this. Okay, and the third thesis will be that an OT typology is analyzed by other OT typologies, which generalize or articulate its grammars. So we tend to think of things as being analyzed by something else, like a segment is analyzed by features or some such. But what we'll actually see here is a somewhat different kind of relationship in which we refer typologies to understand their structure. Let's begin with that idea. So the relation takes place inside the lattice of all typologies. What does that look like? Well, this is not the lattice of all typologies. This is a part of it, a sublattice, which we will investigate somewhat. And more to the point, we'll also investigate a very simple fragment of it, which will show some of the key properties. Okay, so the main issue is this that we're trying to address. A theory classifies phenomena, but how? So consider the positioning of feet in a typical dense footing pattern. In a language in which there are many feet, say crammed to maximality up to, say, possibly up to binarity, possibly completely. And so it happens as that familiarly in odd-syllabled words, the leftover syllable is loose or footed. And I've indicated that by this notation, which I hope you will find perspicuous to save me from going on about it. So I'm just using capital F to mean a binary foot, X to indicate a stressed syllable and therefore a unary foot, and O to represent an unfooted syllable. So then, therefore, we're looking at patterns like this, sequences of feet followed by an unparsed syllable or preceded by one, a monosyllabic foot succeeded or preceded by a train of feet. And so the question is, how are these classified? And as you can see, there's two ways to classify them. So there's the alignment style classification, first noted by Megan Crowhurst and Mark Hewitt, and also anticipated in a work by Paget and Mester on syllables. And then there's the iteration style classification, which came to predominate after in serial theories of stress assignment after its introduction by people like Irwin Howard and C. Douglas Johnson. Okay, so that's simple in that we sort of can identify what the classifying difference is. Now, I just want to point to another kind of issue that arises, namely, consider languages like L1 and L2, and ask the question of what causes the difference in rhythm, namely trochaic and bisyllables and iambic elsewhere in longer words, to emerge. So in the important paper by Alber, which imposed both rhythmic and left alignment constraints, forms like these occur in languages where trochee dominates iamb. In other words, they occur in trochaic language. So they classify with the trochaic languages. How do we learn that? We can't learn that by looking at these forms. The data does not wear its classification on its face. So we have to look a little further into the theory, even than in the first example, and you have to possess a notion of how the theory classifies to be able to make any kind of solid assertion on this point. That's what we're going to be concerned with. Okay, now, this is a general issue, which you might call the paradox of analysis. That is, the more deeply you've analyzed something into finer and finer parts, the less you understand how the parts fit together. So we're never going to describe the flight of a baseball in terms of string theory. Okay, now, returning to the humble subject of the day, we're dealing with a class of modern linguistic theories which all have this character to a degree. Namely, the elements of description are atomized and they're highly interactive. And therefore, it just follows that they have to be descriptively and explanatorily opaque. This means that to understand how to proceed in the theory and to engage in the contentious battle between mighty theories that Kenstowicz was discussing, we have to understand that the theory is also an object of analysis. Just because we have laid down its premises does not mean we understand anything about it. And so this work is distinct from and prior to the betterness struggle. Okay, so this then fits into the analytical program, which was described in more detail in my handout, but I would just like to allude to the basic strategy, which I will exemplify today rather than preach upon. So the idea is that we want to work from simple to complex, and we want to, beyond that, we want to understand and ascertain how the simple relates and builds into the complex. So there's a notion of simplification, there's also a notion of generalization. We'll see that these can part company. In order to do this, we have to show a brazen willingness to simplify. We must deal with things which are not immediately responsive to reality and what we can observe of it. We earn our right to examine a theory X because it relates to a theory Y, and not because it is immediately phenomenally successful. And so how do we... This relates also to a strategy in the analysis of typologies, which I will be exemplifying, that I've been developing in joint work with Birgit Alber. Namely, we seek to analyze typologies into a structured set of choices among mutually exclusive ranking conditions. This is a kind of basis for the typology. By making each choice, you get the languages of the typology. So, in order to do this, in order to approach this goal, we need to begin to ask what the intrinsic classes intrinsically are. So let's do that. So let's take a step back and ask, what does it mean to classify something? So think of a classification as of the elements of a set as a partition. So we have some set of objects tendentiously chosen here to be relevant. And we classify them by grouping them and in such a way that we group everything and there's no overlap of groups. And there's an interesting relationship between partitions or classifications in this notion, which is illustrated right here. Namely, there's a built-in notion of generalization. So here's another classification of the very same set of elements. This classification generalizes the one that we just saw because it has the same categories, or it has a class in it which lumps together two of the other classes. Okay, so just to extend the idea one step, here is an example where we have a class of 6 elements, and there's two very almost trivial classifications. One lumps them all together in one class. One divides each into its separate class, and between that there's a bunch of different ways of classifying them, which I have chosen 2. And we can see that the one on the left here takes A and B to be a class sharing properties, and also E and F, whereas the one on the right takes the class C and D, CD to be sharing properties, and so on. And we can see that how each of the ones in the middle generalizes the lowest one, but they do it in different ways. So they're not actually comparable themselves. Neither is a generalization of the other, although both are a generalization of the fundamental one. And things like this are known, of course, as lattices. And this one goes like so. It runs from the bottom to top, becoming more and more general, and from the top to the bottom, becoming more and more articulated. So these are, I'm going to use these terms because I think they're more suggestive in the circumstances. So if we wanted to talk about lattices, we'd be talking about coarsening, refinement, and about partitions, we'd be talking about blocks or parts. But let's talk about classes, generalization, and articulation. Okay, so what are the objects of linguistic theory that we're going to be worrying about? I distinguish 3. There's a language, an extensional notion, which is a set of linguistic objects, a set of candidates under OT, from each candidate set optimal under some given ranking. Now we have to take a little step here to clarify what the basic objects of the theory are, namely, what is a grammar? So we're going to define a grammar as the collection of rankings, which all give the same language. Very natural. I think it lies behind the common usage. Now, importantly, this collection of rankings has a characterization, a principled characterization, in terms of its structure, not in terms of the facts that it describes, but simply in terms of its formal structure. And this can be given, and indeed is probably most simply given, in terms of the notion of the ERK, or elementary ranking condition. So we can characterize a grammar by a set of elementary ranking conditions, or ERKs, and that gives us an ERK grammar, indeed many. Okay, so what is then a typology? A typology, the notion splits into 2 halves. One is the extensional notion, which is the one that we usually end up dealing with. It's extensional. It's the set of languages. So we figure out what the typology is, and then we rush out in the world and try to figure out whether this or that language is reflected in some piece of reality that we have personally analyzed in the greatest possible level of depth. Or we can also think of it intentionally as a collection of grammars, okay? And we can think of it as, therefore, a collection of ranking grammars, or, if we want to think of it in logical terms, as a collection of ERK grammars. Both characterizations have uses. Today, we will concentrate on the kind of structural insight we can gain by thinking of a grammar as a collection of rankings, which is kind of linguistically repugnant, since it doesn't tell us anything about them. So with that, we come to the notion of abstract OT. with the notion of grammar, we have stepped away from the concrete based on analysis of something or other, and we have got ourselves an abstract object whose properties that we can study. And we know we can do this because a grammar is characterized by an Erk set, and we know what an Erk set is. So let me just briefly remind you that an Erk is a condition on ranking which arises from the comparison between two candidates, the first asserted optimal, and it forms the primary link between theory and data in optimality theory. It characterizes the exact ranking conditions in which candidate Q is better than Z, namely some W constraint dominates all L constraints, a condition of sufficient complexity that it pushes the grammar out of the class of partial orders and into that of the anti-matroid. And if you want to be enlightened on that, you can examine the works of Riggle and Merchant and Riggle. And importantly, the logic of OT is the logic of Erks, and we'll point to cases where that can be used today, okay? So now let's step back and see what we've gathered together before we plunge forward, okay? So we're studying the notion of classification as partition, which comes with a notion of generalization. And that's why we can talk about the lattice of partitions. The lattice is based on the notion of generalization and articulation of those partitions, okay? And the fact is that a typology is a partition of the set of rankings. There's a secondary fact, which we will not dwell on, but which is of use, which is that the set of all possible typologies on n constraints is also a lattice. This is not totally obvious, and I have shown it in a paper soon to appear somewhere. Okay. So, consequence. We have a baseline notion of classification built into OT. So we started out by asking, how do we classify these things together? We look into the internalia of the theory, and we see that right there, without even asking, we have a theory of classification. So what I would like to do today is show the basics of how that works, because it turns out to be not entirely trivial. Okay, so how are we going to do this? Well, metrical theory provides us with an excellent stalking horse, because from the point of view of the analytical program, it admits of a range of simplifications. Although it encompasses a vast range of distinctions, they can be meaningfully simplified, so we can forget about primary, secondary, tertiary stress and just discuss stress and unstress and still have many interesting things to talk about. And so here I articulate the theory that I will be talking about today, namely, it's a fairly familiar one in which feet are binary or unary. Syllables are parsed into feet, or they can be left unparsed. Within that, parsing is free, except that we're going to distinguish among systems, as I hinted at the beginning, where there is some control of parsing in terms of the candidate which is entirely unparsed. So candidates suffixed with O, systems suffixed with O are ones in which we admit a completely unparsed candidate, with X not. And we're going to have 5 constraints here. Again, familiar if contested, but what we're really interested in is the interactions of them and how they illuminate the classification structure that emerges from OT. So the familiar ones are parsed syllable, demanding that every syllable be parsed. I am trochee. To be noticed is how the definition runs, so that the I am constraint dislikes both the binary trochee and the unary foot. The trochee dislikes the I am and the unary foot. Okay, so there's a variety of choices of how to chop up the foot world into constraints. This is the choice that Birgit and I have made and explored. Then we're going to use the generalized alignment constraints, which accumulate the distance of each foot from an edge. And we're going to construct further simplified systems by omitting. We're going to use a strategy of simplification in accord with the analytical program. We're going to omit one of the symmetrical pairs IT and left-right and see what we can learn from those simplified situations. Okay, so this generates a whole class of different languages. So the big mother languages are the ones which distinguish between I am, trochee, left, and right. And the simplified systems have only a distinction between foot type and direction, not distinguishing among those. And for purposes of concreteness, I'm going to restrict that to iambic and left. So this is, with the O, that indicates that we're letting in the nil parse, and we've simplified all the way down to iambic and left and so forth. And then there's the various intermediate systems, which are worthy of contemplation. Okay, so what do we get from these systems? Well, from the one where we have no completely unparsed form, we get three languages, which I've spelled out the forms here and given them highly mnemonic names, which I hope will carry you through the day. So there's the sparse language, which allows just one foot. There's the weakly dense language, in which all feet are binary, and therefore in odd syllables we have a leftover unparsed syllable. And there's the strongly dense languages, in which everything is always completely parsed. Okay? If we let in the completely unparsed language, and when we simplify down here, we get this. Sparse splits into two kinds depending on the treatment of monosyllables. So in sparse.o, the monosyllable is not stressed, it is unparsed. In the language sparse.x, it is parsed, and everything else is the same. So those are the prosodic systems we're going to study, and the criterion that we're placing on them is they have enough rapport with reality so that what we learn will not be utterly fantastical in our minds. Okay, so we were talking about the lattice of partitions. Okay, these guys are partitions on the set of rankings. What does that look like? It looks like this. This is the lattice we get from the system, the four-language system, which allows unparsed forms. And so we can see the pattern of generalization as we go up the lattice, right? So for example, there are two types of dense languages, weakly dense, which are labeled here dense.x, and dense.o rather, and strongly dense, labeled dense.x. Notice as we ascend the system, this becomes the category D, dense. The two sets of rankings that encompass density of footing correspond to one language in this abstract typology. And as we go further, we see that we can also join the sparse ones, and then this gives us a two-language typology, generalized, which analyzes, as I promised, the languages of the root typology. We go up here and do the same thing, and then we have the distinction between those which allow and those which do not allow the unparsed monosyllable. Okay? Now, how do we get analysis out of this? Well, what we do is we take these two guys and we find their minimal mutual articulation. In other words, we find the typology which is an articulation of both of them into and only articulates as far as it has to. So we can see here that sparse over here and O intersect to give us sparse.o. Dense and x intersect to give us dense.x. And that's generally how it's going to work. So we end up with an analysis that looks like this. So the analysis of the typology is these other typologies. And we can see how they come out in these forms here. So this typology, a two-language typology, is characterized by the negative Irk pair given here, or translating into the choice of ranking conditions, parsyllable dominates IM dominates parsyllable, and so on. Okay, so we want to do analysis. We want to figure things out. So we have to navigate the typological lattice. How do we do that? The first observation to make is that going down is easy. If we know the things up here at the top, we can easily construct their minimal mutual articulation. Simply, if we have their VTs, their violation tableaus, we can simply lump them together, and that will be the violation tableau of this. So we have the Irk sets. Similarly, we lump them together. That's going to be the Irk set of this. So there isn't any problem going down. But there is an issue that lurks with this observation, namely, we actually need to go up. We start at the bottom here, and we're trying to analyze this typology. So we've got to climb up here to get to the primitives of the analysis. So we're going to devote some effort into how to do that. The first observation to make is we can go up using a logical operation on Irks known as the merchant join. So what it does, it's a combination of the components of the ERK vector, like fusion, except that the mode of combination is the 3-valued version of OR. So it's like, it's related to the idea that P entails P and Q is sort of the minimal, P or Q. P entails P or Q. P or Q is the minimal form that is entailed by both P and Q. So what we get here is the minimal language, which embraces both of the joining languages. Now, problem, this need not be the simple union of the rankings. It can be bigger because sometimes having different rankings, putting them together entails that you must have other rankings to flesh things out into an authentic grammar which has an ERK set. So we can distinguish conservative joins, which are good in that we join two languages and they include nothing but what was in them. And we can also, but unfortunately not all joins are conservative. And we can also go one step further if we look a little harder and we see that not all conservative joins are typological, in that just because you join two languages conservatively in a typology doesn't mean you get a typology in the output. An interesting point which we'll save for later. Now, what's the solution to this problem, this analytical problem? The solution lies in understanding the geometry of optimality theory and going beyond that geometry to seeing how the fundamental notion of order in the theory imposes an order structure on that geometry, which then completely determines how you generalize. Okay, so what's the geometry of OT? It's given by this fact. There's a natural notion of adjacency in permutations. So if you have two permutations, consider that to be a sequence of stuff, right? So P, A, B, Q is a sequence of things, constraints, of which A and B are constraints and P and Q are sequences of constraints. If we have another permutation, which is identically the same except for the switch of the pair A and B, then those are said to be adjacent. This is standard and lifted from the literature on the symmetrical group and the study of permutations. Okay, now the fun begins with Arthur Cayley when we know how to lay these things out, lay out this notion of adjacency as this very abstract algebraic notion of adjacency as geometry. And this is something which has been noticed and explored by Rigel and a little bit later by MIT's own Igor Yanovich. Okay, so we're going to extend this rendering to the analysis of typologies as follows on the basis of three facts. One, a grammar is a connected region in the geometry of permutations. In fact, to add a nice word to the discussion, if you take the entire set of permutations and arrange it by adjacencies, exactly like that, you get an object known as a permutohedron. Discovered about a century ago in France and causing quite an argument about the name. Okay, so fact, a grammar is not just a bunch of rankings scattered all over the permutohedron, it's concentrated in a region. Secondly, a typology partitions the permutohedron into regions. And therefore, we can lift the notion of adjacency from that of the single rankings to whole regions. So two regions are adjacent if they have border points, namely one point or ranking in one and the other in the other. Okay, so what does this look like? Let's get some physical grasp on it. So here's the permutohedron on 4 constraints. And here's a picture that I made myself. This is the furry permutohedron. And it is intended to show the intrinsic structure of it, namely to bring out the fact that it's made up of a bunch of hexagons. Okay? So this is on 4 constraints. It has 24 vertices. Why hexagons? Well, they have 6, 3 factorial, right? So you take the hexagons of the three permutohedron and you kind of glue them together, and then that gives you this figure. And if you want to go up to the 5 constraints, you take this guy and you glue it together in a completely analogous fashion in 4-dimensional space, which is, in fact, where we'll be operating to a degree. Okay, so Of course, today we will not be flying around much in four-dimensional space. Let's go back to 2 dimensions, okay? We can learn everything we need to know there. So this is the permutahedron on 3 constraints, the permutagon, a simple hexagon. And indeed, this is the representation of our system, our highly simplified system of 3 languages, which contains a sparse language, a weakly dense language, and a strongly dense language, caused by collapsing the distinction between iambic and trochaic feet and the distinction between left and right alignment. So you might ask yourself, what is this language sparse? Where is the damn foot? Is it left or is it right? Is it iambic or is it trochaic? This is not a question you can answer. We have lifted those distinctions, and we're just focusing on the fact that it is sparse. So there's no candidate of a concrete type is going to characterize this because, something's either left aligned or right aligned. It's either iambic or trochaic. But when you class things together, you lose the ability to make those distinctions, and that's exactly what classification is, the loss of certain distinctions. Okay, so you can now see how this permutahedron is constructed very graphically. You might not have been able to completely parse the truncated octahedron we were just reveling in. So if we look at this, we see that we can begin over here at the the right border of sparseness, which has the constraint IM dominating AFL dominating parsyllable, and its nearby neighbor is obtained by flipping these 2 guys, one neighbor. We flip IM and AFL, and that gives us, great. Okay. No, let's not do that. Let's flip AFL and parsyllable. Okay, and that flips us across the border into weakly dense, IM, parsyllable, AFL, okay? And if we go around in this circle flipping things, we're going to go from neighbor to neighbor to neighbor to neighbor, and sometimes we cross the border from one language to the next at the border points, okay? So, great, so we have this gigantic permutahedron with a zillion n factorial vertices, and we can arrange it into regions, and we can see how the regions are connected. How do we make sense of that? Well, we use the simple dodge of shrinking each region to a point, because that's the points we want to talk about. We want to talk about the languages. That's what we do, okay? So this is the geometric diagram that is truly relevant to the analysis of this simplified generalized typology. So what have we done? We've taken the actual permutahedron, located the regions that are languages, and we have shrunk them to points. So each region retains all its external connections, but all the internal guff is lost and mashed together. Okay, so that's how we generalize over all those rankings to get the language. So this is just a geometric analogy of what we always do when we talk about a language. Okay? So, having done that, we can now return to the question of classification. So the natural sense of classification is, before we do that, I wanted to entertain you with some permutahedra, some that have been shrunk to points. So this is the 5-dimensional permutahedron, 120 vertices, with the languages of our 21 language system located on it as regions, and so each one is connected as shown here. Connoisseurs of dimensionality will notice this is basically a 4-dimensional object, like a cube with other stuff traipsing through it. Now the other stuff that traipses through it will disappear if we simplify the language, the gen, to consider not letting ourselves have unparsed forms except for the monosyllable. So if we only allow unparsed monosyllables, this is what things look like. In other words, it's a perfectly cubical system. Although, as we'll see, though, the way the parameters form is going to be somewhat more interesting. Now, if we then toss away all completely unparsed forms completely and begin again with a system of a theory of stress based on that, then things simplify yet further, because what happens is we lose the distinction in the sparse languages, which can only occur in monosyllables. So we throw away the monosyllabic distinction, bing, they close up, and we get this geometry. And if we apply the analytic program and engage in a brazen application of the will to simplification, this is what we get. And of course, this is what we'll look at. Okay, so this is the language we're interested in looking at. And we ask ourselves, how do we classify things geometrically? Well, the natural way to do it is by adjacency. So we can have groups of adjacent vertices in this geometry. So sparse and weakly dense can classify together as opposed to strongly dense, and so on and so forth for any two against the three. Okay? So let's make an interesting misstep. Let's try to classify these two together. Geometrically, any adjacent pair can be a possible class. Try these. Let's join sparse and strongly dense and set them against weakly dense. So we have a contrast in two defining properties here. But we have another way of looking at things through the lattice of typologies, right? So what have we done? We've wandered off to talk about geometry and what it tells us about classification, and now we abruptly remember that we already have an intrinsic theory of classification in the system, namely the lattice structure, which we can construct. And when we do that, we get the lattice for this language, and we examine the classes, and we notice to our horror that the class that we just hypothesized is conspicuously missing. So this is a geometrically possible class which does not show up in the natural classification of typologies. Okay? So now we enter the final phase, when we will see the key aspect of typological structure, which determines how the languages can be classified. So we talked about the adjacency relation in purely geometric terms. These things are structurally adjacent, as in the pictures we looked at. Okay, but we are dealing with lexicographic optimization. The order makes a difference in how good its objects are compared to other objects. Therefore, we find that when we push from geometry into OT itself, we discover that the adjacency relation imposes an order on languages and grammars when the two rankings belong to different grammars, that is to say, when they're border points for different regions. And particularly, it works like this, which is actually not as unintuitive as it is dryly presented. So here we have our two neighboring points. One of them delivers language 1, the other delivers language 2. Okay? And this turns out this can only happen if language 1 is in this order better than language 2. Big surprise, right? So on the constraint A. So the constraint A is the one which is doing the job here, ejecting language 2 and favoring language 1. The constraint B in the inverse here is doing the job for language 2. So that gives us an order that relates two languages, two entire languages. Okay? And on top of that, there's an equivalence, because inside the prefix P, all these L1 and L2 must be exactly equal. Otherwise, they're just not going to make it through the prefix, right? Because if you're going to go through an OT filtration and you're going to pass through a constraint together with your buddy, you've got to both have identical numerical violations, or one of you leaves. Okay, good. Now, this seems utterly crazy. How could it be that languages are ordered by OT? OT is about candidates, right? It turns out, however, that every single typology in OT, considered as a set of rankings, considered as a set of grammars, can be derived from a single typology, from a single violation tableau. Now, why is this puzzling? Well, because in concrete OT, we often need a bunch of different candidate sets to get the typology. In fact, part of the art of doing OT properly is to get enough candidate sets to actually generate the typology, okay? And for some systems, you've got to have more than one. In some simple concatenative systems, like the theory of syllables, you can take a word long enough that it has every configuration, they're independent, that will give you the whole typology. In other areas, probably more generally, you need several concrete inputs. For example, in stress theory, there is no candidate that is both monosyllabic and tetrasyllabic. Yet you need short and long forms to generate many kinds of typologies. You need even and odd forms as well in many typologies, but there is no candidate that is even and odd. So how can it be possible that there is out there, assuredly, a single tableau that gives you every typology, including the ones, whatever ones we were just talking about? So this is a result which I show in a paper called One Tableau Suffices, and it shows that every typology can be derived by a single VT. And we won't have time to review it, but what happens is rather simple. Given several VTs, you form the Minkowski sum of those VTs. You add, you make a sum by adding the violation rows, one from each VT, and add every combination. That gives you the tableau, okay? But the rows of this UVT, this unitary VT, which describes the entire typology, are really languages. And we know that and given a violation tableau, each constraint imposes order and equivalence on the columns, right? So what are the rows? Most of the time we talk about inputs and outputs. Here we're talking about actual languages. What does this look like? It looks like this. Here is a unitary violation tableau for the typology of maximal interest today, right? And this is in fact a language where you concretely must have more than one input to get its typology. How do I arrive at this? Simple. I depressed the button that said Minkowski sum in OT Workplace. And boom, out this comes. I check it, it works. When I first happened on this, let me tell you of my astonishment that it actually worked, but it does. Okay, so now we arrive at the key question. There are many unitary violation tableaus that will produce any given typology. Why is that? Because we have this violation tableau with numbers on it. Pick some different numbers. That doesn't guarantee a different result, right? If we retain the ordinal structure of the columns, we get the same result trivially. But we can do all kinds of other things as well and still get the exact same typology of grammars. So the immediate and fundamental question is, what do all of these guys have in common? This vast, swirling collection of unitary VTs, which give us a typology and impose a variety of order structures on the languages. And the answer is, they have in common the order and equivalences that are the same in every single one of them. So you just go through every single one of them and note which things are identically the same, and then put those together, and that gives you the structure that each one of them must have. Now, this might seem like a daunting task, there being a innumerable infinity of such things. However, it turns out that the order and equivalences we are seeking are exactly the set of orders and equivalence relations that are disclosed by border point analysis. So we just look at the border points of the typology and see what they tell us about the relationship between the languages that lie across the border. Which one is better than the other one in this order? And that will completely determine every single UVT that describes the typology. So Merchant and I call this the moat. So each typology has a unique moat. So what is the moat? We'll see in 1 second, but let me just advertise its properties. First of all, the numerics of every unitary violation tableau accord with the order and equivalence relations that are in the moat. That's why it's called the mother of all tableaus. You consult this object, and it tells you everything about every numerical representation of the typology. Furthermore, every typology has a unique moat, and every moat has a unique typology attached to it. And the moat then consists of single order and equivalence structures that we call EPOs, namely equivalence augmented privileged orders, and one for each constraint. So the EPO is really the essence of what the constraint is, much more than the numbers that assign. It says what the constraint is in every imaginable realization of the typology, which has exactly the same grammars. So what does an EPO look like? Here's the moat for the typology that we're interested in. And here's the EPO for parse syllable, for IM, for all feet left. In this, order is shown by the red arrows and equivalence by the double blue lines. So this tells us we get exactly this typology as long as we pick numbers that accord with these relations. Small, bigger, bigger. Small, the same, bigger. Right? Small, bigger, bigger. This tells us something interesting already, even though the example is simple, namely that we can, as long as the numbers assigned to weakly dense and strongly dense are less than the number assigned to sparse, we get the typology. These stand in no particular relationship to each other. Okay. Now let's use this. We're going to use this to determine all classifications that are possible of all typologies. So we have this three-language typology. I took a generalization of it that joined these two guys and looked at this guy, and then I constructed the moat for this typology. And what I'm looking for is that it comes out, bravo. Okay, so what did I do? I constructed the moat for the classification of the sparse language versus the two dense languages. Okay? And I want to know, is this a legitimate typological classification? The answer is, well, we know from our basic finding that typologies classify typologies, that this must be a typology. Therefore, it must have a moat. So what is its moat? Its moat looks like this. Where do we get this moat? Have we laboriously been spading around in the background? No, we get it directly from the moat of the underlying typology we're trying to analyze. We simply take the nodes and fuse them together. We merge these nodes. So this derived moat is obtained by simply taking the nodes SD and WD, merging them, and keeping all external relations. So we know that this derived class stands in an order relationship to sparse because one of the external relations of one of its members does. We know that this derived class is equal to sparse because one of its members has an external relation to sparse, which is preserved by simply the internal joining. Now, we can now answer the question that we set out to look at, namely, what about the geometrically feasible but non-typological breakdown that joins these two guys together, sparse and strongly dense as against weakly dense? When we apply the procedure, this is what happens. If we try to join sparse and strongly dense and retain all external relations of the participating members, we get a cycle, which corresponds to an order contradiction. One member of the joining group says that you must be less than numerically the other language. The other one says you must be greater than. This cannot be realized as a tableau. And here's another case where equality and order bump into each other. Here we escape by the hair of our chinny chin chin. Okay, so that explains why this geometrical classification doesn't work typologically, because there is more than geometry, there is order. As we have explicated, this order is represented as the moat and its epos. Okay? So what is good about moats? A hypothesized class is typological if it belongs to a suitably generalized typology. That happens when we have an moat we are analyzing, which merges down to a valid moat which carries the generalizations. How do we represent this class that we've got by fiddling with this diagram? Well, that's very easy. We can either calculate directly from the diagram, or we can use the merchant join on the languages, represented as Irk says. Okay, so this means that we've actually solved the problem that we set out to solve. We found it was easy to go down to articulate, hard to generalize, and we now know how to generalize. And we can obtain every possible typological generalization that the system implies. So we have gained complete knowledge and made no Faustian bargain. Okay, now to conclude, I would like to use this as a tool to try to convince you that even in complicated circumstances, the simplicity of the construct allows us to make interesting observations. Namely, the language we've been studying, the typology we've been studying, the three-language typology, is a simplification of the grand 21 language typology, but it is not a typological generalization of it. there is a difference between simplification and generalization. Why not? Well, we need nothing more than root around in the moat and its epos. Fortunately, we can focus in on the problem. But one thing I would like to note in passing is that this is 4 of the 5 epos for the 21 language typology. And note that the moat declares with utter transparency the symmetries revealed by the constraints. So that I am and trochee, their utter symmetry is laid unmistakably before your eyes as you cast them over these diagrams. Similarly, the symmetry between the alignment constraints is laid before your eyes in these diagrams. This obviously motivates structurally and formally the kind of merger that we indulge in analysis. Okay, so let's figure out what the problem is. Well, this is the articulated full language. What happens to the category weakly dense in the simplified typology that analyzes this? Well, we notice that in the EPO here, as it happens for IAM, the category weakly dense is broken up into 4 pieces. If the simple typology, which has one piece labeled WD, is going to be a generalization of that, we've got to be able to merge these 4 and produce a moat. Well, this is not going to happen. You can see that right away, right? Because there's the 4, but the merger is obstructed by nil. You cannot get through nil without creating a cycle in which nil equals these guys and is less than or better than these guys. Okay? So this tells us, and the same argument can be applied to sparse, this tells us that there is something more going on in structure than simple typological classification. And that the behavior of nil, which is determined by the order structure, comes because the class nil does not support the distinctions that sparse and weakly dense do. So there's an actual strategy we can use to recover from this by breaking nil up into 5 pieces, giving us a richer derived tableau typology, which we can then climb up back, yielding the merchant join. I mention this in passing to show that there is a region of generalization that we would be interested in next going to understand why certain simplifications are authentically simpler but not authentically generalized. So that what that means is we have made the first step in the direction of understanding the notion of generalization in typologies. And after this first step, there are others. The first step tells us where the others are. And therefore, I conclude that having made this first step, a bright future beckons that will be built upon it. So what are the theses that I advanced at the beginning? Well, I said that an OT typology is intrinsically analyzed by other OT typologies which generalize or articulate its grammars. I said that an OT typology comes with an intrinsic geometry that influences how its languages class together, and that it comes with an intrinsic order and equivalence structure on all the languages of the typology that determines how the languages class together typologically. And that is the conclusion of today's work. Thank you. Yeah, okay.
So we unfortunately have no time for questions, but we can have discussion during the break.
Or not.